are going to start chapter 4 on exponential and logarithmic functions. For lesson 4.1, some key things we want to be on the lookout for. So applications of exponential growth functions would be for finance, internet, DVD players. These are examples that will be seen either in the lesson, in the activities that we do, or in your textbook. Some vocabulary that we want to be aware of. Let's scroll this down a little. Oops. So you can see this. So key vocabulary, it would be exponential functions, exponential growth function, growth factor, and the word asymptote. So that's going to be important as we talk about graphing. So let's take a look at graphing. How do we do this? So normally, when we are graphing a function, let's see if I can show you the screen a little bit. Can't see the example. Oh well, we'll look at the example from here. Let's get into our pen. We'll go with nice and thin here. I like blue. All right, so normally when we see a function, it is in the form of y equals b to the x. Okay, this is called an exponential function. It's this function because, well, the parent function would also include, of course, our coefficient of a. So a, of course, can't be equal to 0, because otherwise everything would be equal to 0. And b has to be a positive number other than 1. So b needs to be greater than 1. And then x can be any real number. Okay? So notice now, we've always dealt with x being part of the terms, but now it's the exponent. When we're graphing a function like this, we graph it the way we do any other function. Make your table of values and plug in the x values to see what the y value would be. So of course we can always start off with our normal ones. Get back into practice of writing on this board. Now remember that this x value is the exponent. So, for example, if x is equal to 0, alright, that means 4 to the 0 power. Well, anything raised to the 0 power is 1, so your y value is equal to 1. So, starting on the left-hand side, if x is equal to -2, that means 4 to the -2, which means 1 over 4 squared. Notice that this is not a negative number. This is just 1/16. Alright, 4 to the -1 would be 1 over 4 to the first, so 1/4. If x is equal to 1, that's 4 to the first, so that would be 4. If x is equal to 2, 4 squared, so 4 times 4, 16. You oftentimes hear things talk about growing exponentially. Alright, you'll notice, as we do with exponential problems, the higher your exponent is, the bigger that answer becomes. So it grows very, very quickly. Let's go ahead and graph this. So let's graph 0, 1, nice and easy here. 1, 4. And 2, 16, we're not going to be able to reach because obviously that's way too high. So let's go with -1, which would be 1/4. And -2, which would be 1/16. I'm kind of just guessing it's about there. Again, we want to be as precise as possible, but not too crazy worried about it. Now, graphing from left to right, we want to draw our curve to follow that. Now, as you're graphing that curve, notice that as it goes to the left, as x gets greater, alright, so as x approaches -infinity, alright, our y value doesn't actually get any smaller than 0. It approaches 0, becoming smaller and smaller and smaller as a tiny, tiny little decimal because of that negative exponent, but it doesn't actually ever reach 0, nor does it go below 0. So we call this an asymptote. An asymptote is a line that is basically a barrier on the graph, that the y equals The y equals 0 would be our asymptote. Our graph is never going to cross over that. Now, as x approaches positive infinity, y can be as great as it wants to be, all right? Because it's going to go as high as those values will let you. So when we're talking about our domain and range, remember domain would be your x values. So here, x can equal all real numbers. So we'll say all reals. But for our range, we are limited. Y is going to be greater than 0. Notice that it's not greater than or equal to 0, it's just greater than 0. Okay? So let's clear that off and take a look at our next example. It wants me to. There we go. Alright, come on, cheers. Oh, I gotta do it as nice. You know, we've been on holiday. I forget how to do these things. Apparently it does too. There we go. There. Oh, finally. Goodness, that took a while. Okay, so now we're looking at a new function. We got a couple of functions here. So before we had the a was equal to 1, the coefficient was 1. But now we're going to take a look at what happens when we have different coefficients or different b values. Alright, again, we have a general idea of what the graph is going to do. As x approaches positive 0, the graph is going to increase to the right. As x approaches negative infinity, the graph is going to approach 0, but not actually ever touch it. Really, all we need to do is worry about the first two main points. So let's figure out what y is equal to when x is equal to 0 and when it's equal to 1. All right, two main basic points. So we already know that if x is 0, then y would equal to 1. Anything raised to the 0 power is equal to 1. And if x is equal to 1, then y is going to be 4/3. We're graphing this first function over here. So a little more than 1, about 1 1/3. All right. If you want to, you could always say, well, what is it when x equals 2? If you want to get it slightly more precise. So that would be 16/9. So almost 2 here. All right. So we can see that this is approaching rather gradually. And then as we go to the left, again, you want to try and make your curves as neatly as possible. Well, zeros here. And so, again, it's going to approach 0 as x becomes negative infinity and continue to approach positive infinity as x approaches positive infinity. All right, let's change the color. I'm going to keep that graph up here, but I want to use a different color for the second graph. So let's make it green. All right, so we have negative 1/3. So this negative gives me a big red flag that tells me the graph is going to flop directions. It's going to now go the other way than we're expecting. Let's go ahead and still focus on x equaling 0 and x equaling 1. We're going to do this as a table. That's fine. So we already know that if x is equal to 0, that means 3 to the 0 is 1. 1 times negative 1/3 would be negative 1/3. All right? If x is equal to 1, then 3 to the first power would be 3. Negative 1/3 times 3 would be negative 1. So that gives me 2 points to work with. If you want to figure it out for x equals 2, that's fine. 3 squared is 9. Negative 1/3 times 9 would be negative 3. So go ahead and plot these points. So 0, negative 1/3, 1, negative 1, and let's say 2, negative 3. So we can see how steep that curve is. So again, we're going left to right, and even though this is negative, as x approaches negative infinity, y is going to be approaching 0. It's never actually going to reach 0. All right, let's talk about the domain and range of both of these forms. So the domain all the x values, of course, for both of these, the domain is equal to all real. All right, now let's talk about the range. Well, the range for example A, right, this is the y values. Well, we can see that y is all positive, so y is greater than 0. That's the range for the first example. Now for example B, notice that our y values are all negative. So the range would be the y values saying less than 0. And again, I noticed on your quizzes from last unit and also the prerequisite quiz that we did in class, when you're writing the range values, all right, it's always x or y, then the inequality sign if there is one, otherwise it's all reals, then the number, all right? Yes, technically 0 is greater than y is equivalent, but that's not how you write it. It looks very awkward to do it that way. So go ahead and write the variable first, then the inequality symbol, then the number. All right, so let's clear this off. Click onto our mouse and take a look at our next example. All right, so now we have, I'm going to get back into the blue because it's easier to see. So now we have an example where we have our parent function and we're going to make some transformations. So it's kind of hard to see with the way the screen is working, so let me rewrite this for you. All right, notice that you see H and K. So H tells us if we're moving left or right horizontally, and K tells us if we're moving up or down. Tells us the vertical shift. So the first thing I want to do is I want to go ahead and graph this function without the shifting. All right, so let's take a look at what it is if I were to graph 2 times 3 to the x power. Okay, now again, these are exponential functions, so this is separate from this. It is not equal to 6x, or 6 to the x power. It would be incorrect. So let's set up our table of values here. So we have 0, 1, and 2. So 3 to the 0 is 1, 3 to the first is 3. Oops, except we're doubling this. So this would be 2, this would be 6. 3 squared is 9, 9 times 2 is 18. All right, that's going to be a little too big. So go ahead and graph. We have 0, 2, and we have 1, 6. 1, 2, 3, 4, 5, 6. My lines are a little hard to see. All right, and then 2 to the 18th, which is kind of far out there. So 2, 2. And let's kind of graph it out that way. Okay, so that's the normal graph, but we have an H and a K here. So let's figure out what H is equal to. So -2, and K is equal to -1. So H equaling -2 means left 2 units. And K equaling -1 means down 1 unit. All right, so quickly let's change the color of our pen here, and I'll show you what these changes look like. I'm going to go with red. Okay, so let's take the 2 points we did. We had 0, 2, and 1, 6. So I want to go to the left 2 units and down 1. So here's my new point. And then go to the left 2 units and down 1. So here's my new point there. And then I'm going to go ahead and graph this out. So going left to right. Now also notice that because there is a K value, our asymptote is no longer y equaling 0, right? Because we've shifted the graph down. Well, if we shift the entire graph down, that means we also shift the asymptote down. So now your asymptote is going to be at y is equal to -1. So the domain would be all real numbers, and the range would be y is greater than -1. All right, let's take a look at some practice problems. Actually, we're running out of time, so I'll start off the next video with practice problems and the final example.